Hey, this is Tasman. I'm going to take you through a question from Accelerated Physics 2 on circuits. So we're given this circuit here. It's got battery with electromotive force E, a capacitor with capacitance C, and a resistor with resistance R. And the question is this. Once we close the circuit, we need to find the charge Q on the capacitor as a function of time. So, we're going to close this switch here, and this battery is going to start pushing current clockwise around the circuit. This way, current I. And so current's going to start flowing this way through the circuit, and positive charge is going to start building up on this left-hand plate of the capacitor. And we'll write that charge as Q. And so Q is going to be increasing as the current comes along here. And on the other plate, charge is going to be sucked around in the clockwise direction. So we're going to actually have a negative Q on the other plate. And so what we need to do is we need to find this Q as a function of time. And so how do we do that? Well, what we're going to do is we're going to use what we know about circuits to write a differential equation involving Q and T. And then once we've got that, we can solve it to get Q on one side and a function of T on the other side. So, what do we know about circuits? Well, the first thing you should remember when you see a circuit like this is that the sum of the voltage differences across the different components must always equal 0. Now, why is that? Well, if you pick any point on the circuit, say here, and then you move clockwise with the current, and you add up the voltage difference across here, the difference across here, and then the difference across here, and come back to the point you started at. If that sum of voltage differences did not equal 0, then you'd end up with a voltage difference between this point and itself. So that doesn't make any sense. And that's why the sum of the voltage differences always has to be 0. So let's write down the voltage differences. The differences. So the voltage difference across the battery is given to us. It's just E. So that's nice and easy. What about for the capacitor? Well, we know by the definition of capacitance that C equals the charge on the plates Q over the voltage difference V. And so, here's our voltage difference. So we can rearrange this equation to get V equals Q over C. And so that's the voltage difference across the capacitor. Let's write that in. And lastly, across the resistor. Well, we know by Ohm's law, that V equals R, the current I times the resistance R. And that's our voltage difference. So let's write that in as well. I R. Now the reason I haven't written these out in the form of an equation yet is we have to worry about the signs. So, how do we know which ones we write as positive and which ones we write as negative? Well, here's the rule. If that component helps the current, if it pushes it along, then we write the voltage difference as positive. If it opposes the current, if it pushes it back, then we write that component of the voltage difference as negative. So first, the battery. Well, the battery is what's helping the current forward. So we write that as positive. E. What about the capacitor? Well, current's flowing along here, and it's building up on this plate. And as it's building up, it's getting full. And the more it gets full, the harder it's going to be for more charge to flow into there. So it's actually opposing the current, which means that voltage difference is going to be negative. So let's write that in as negative minus Q on C. And what about the resistor? Well, the resistor is resisting the charge, right? So it's going to come along here. It's going to provide a force opposing the current. So we can write that potential difference, IR, as negative as well. And, as we said at the start, the sum of these voltage differences must be 0. So we have a really nice little equation here, but it's not quite right because not all of the variables in this equation are Q or T, and that's what we need. Specifically, we've got this variable current I that's not in terms of Q and T. So how do we write it like that? Well, the current is the amount of charge passing any point on the circuit per second. So say we picked this point here. The amount of charge flowing onto this plate per second is I. But that's also the rate of change of Q. If I is really big, then Q is going to get big really fast. But if I is really small, then Q is going to get big very slowly. So what does that mean? Well, let's write it in a different little box up here. It means that the current I is actually the rate of change of Q. So let's write that here. I equals the rate of change of Q, which we can write as dQ dt. So now let's substitute that into our nice little equation. E minus Q on C minus dQ dt R equals 0. And now this is actually a differential equation that you can solve. It's a separable differential equation. And if you're not comfortable solving these, then you can go look at our section on that. But if you are, this is what you should end up with. You'll get Q on one side equals EC, and then in brackets 1 minus e to the power of negative time on RC. And when you get an answer like this, you should always check that it's reasonable. So say we sub in t equals 0, we get 1 minus 1, which is 0, which makes sense because at the start when t equals 0, the charge on the plate should equal 0. And if we take as t goes to infinity, this term here will actually go to 0, which means that the charge on the plate will level off at a certain value, the value being E times C, which makes sense. Once this plate starts filling up too much, you'll end up not having any more current flowing into it. It just won't be able to. It'll be too full of charge. So that's how you solve a circuit like this. Thanks so much.